Hello, I'm Artyom Shamsudinov, and here's a brief introduction of the Beyond Decentralized technology stack. Beyond Decentralized is a new nonprofit company meant to facilitate creation of open source software. The mission of Beyond Decentralized is to enable fair data ownership and independent software development. By fair data ownership, I mean everyone should be in the custody of their data. A person should be in control of his or her individual data. A family should have joint control of its data. Data that belongs to a community should be in the custody of that community. Independent software developers should be able to write applications of any size that would add value to existing software ecosystems. Back in 2015, I wrote a family organizer called Hans the Organizer. As soon as I finished it, I realized that other families would have to store their data on my server. That didn't seem right, so the following year I started writing software that over time grew into Airport. Now, in 2022, I realized that this software can help to create an internet of independently operated databases. At the core of Beyond Decentralized Stack is the idea of how to take a database and split it into pieces. What I came up with to do that is called Autonomous Interdependent Repositories. AIR is a way of storing virtual repositories in a relational database. It keeps track of records with a multi-key ID scheme. This allows each repository to be recorded in its own transaction logs and shared separately. So a repository is fully autonomous and can be used on its own. Yet, at the same time, repositories can be interdependent and can be used together. Repository data is stored in standard relational tables. For example, a repository for event A contains a record in the events table that keeps track of the event. It also contains records in the posts table that keep track of the conversation associated with that event. Thus, the event A repository spans both of those tables and contains all of the information associated with the event A. In other words, the record of the event and the records for the conversation associated with that event are stored in one virtual unit. From the point of view of the database, this unit is just a collection of rows across two tables. Repositories keep track of their records separately from other repositories located in the same physical database. To do that, the primary and foreign keys in all relational tables for AIR are composed of three identifiers. First is the repository ID. It is just a globally unique identifier for the repository itself. Second is the repository actor ID. It represents a particular user on a given device using a given application. Third is the actor record ID. It uniquely identifies a record in a given table for a given repository actor. In practice, it is a database sequence number for a given table in the database where the record was created. Traditional relational databases maintain a common transaction log of every modification made in a given database. In AIR, every single virtual repository maintains its own log of transactions. Copying a given repository to another database is done by rerunning in the receiving database all of the repository transactions in its transaction log. Thus, sharing a given repository is possible without having to share all of the data in a given physical database. What relational databases are really good at is keeping track of relationships between different pieces of data. Traditionally, it has been hard to decentralize or even distribute relational databases because the data in them is so interconnected. In AIR, if a given repository references records from other repositories via foreign keys, those records are copied into the given repository. This makes duplicate copies of records for the purpose of making repositories fully autonomous. Thus, a given repository contains all of the records from other repositories that are referenced from its own records. If the records copied from other repositories reference additional records, those additional records are also copied into the given repository. This allows the repository with references to records in other repositories to be usable in other physical databases. In other words, this allows UIs to build complete data views of a repository, even if it references repositories that are not present in the local database. At the same time, repositories are interdependent. Every foreign key relation in AIR has two sets of keys. The first one points to the record inside the same repository. If that record originally came from a different repository, that's the copied record. The second set of keys points to the true source record. That source record may be in a different repository. When querying AIR data, the applications can either ask for the repository copy of the data or the original source data. AirReport then chooses the appropriate set of keys to use for the joins in the application query. Applications can also make observable queries that first return the repository copy of the data and then, in the background, progressively load the original data. This is possible because a repository keeps track of all of the repositories it references and of all the locations where those repositories can be found. The founding and core project of Beyond Decentralized is AirReport. It implements AIR and provides a framework for using repositories. It takes a relational database, wraps it in the necessary code to make AIR work, and makes it deployable on user devices. Airport works in internet browsers as a dedicated browser tab. It can also work as a native application that runs on a phone or any other personal device. All applications that use the same airport installation can interoperate and access the same data. The data itself is not stored by the applications and stays on user devices in the airport database. Airport is in charge of sharing that data with airports that run on other devices. It can share data via decentralized file systems like Filecoin, or other means of sharing are possible as well. For example, sharing via peer-to-peer connections. Airport provides a number of features for application developers. A core feature is an Object Relational Mapping Framework, also known as an ORM. Airport's default ORM is Tarmac. It is possible to write other ORMs that would use different styles of accessing data. Tarmac draws inspiration from Java's Hibernate and QueryDSL frameworks. Unlike Hibernate, Tarmac does not maintain a database session. This means that Tarmac entities are always in one state, and there is no need to attach objects to or detach objects from a database session. Tarmac entity objects have an original state property. This is where Tarmac keeps track of the modification state of entity objects. That makes it possible to make entity object modifications in invoking applications or in single-page application user interfaces. No matter where or when the modifications to entity objects are made, Airport will figure out what fields need to be updated based on the original state property attached to every entity object. Tarmac maps entities to relational tables with TypeScript decorators on class definitions. This is a tried and true way of mapping entities, very close to what's found in Jakarta Persistence API, or JPA. Tarmac aims to make it easy for developers to transition to Airport. Tarmac integrates SQL into TypeScript. It takes advantage of JavaScript's ability to declaratively specify objects. A SQL statement is represented as a JavaScript object. Special query objects are generated from entity declarations that you saw in the slide before and are used to construct query logic. Tarmac select statements declare the select clause as a JSON tree with entities nested according to the many-to-one and one-to-many definitions in the entity objects. The flat SQL result set is converted to an interlinked object graph. Here, the open and closed curly braces after the children property mean that Tarmac will return child entities with all of their own properties included. This will include the child entity's many-to-one link to the parent entity. That parent entity object will be the same object as the root object of the query result. Tarmac also supports the traditional way of defining the select clause and flat result sets. Query type safety and auto completion is provided by Tarmac's data access object or DAO layer. A key technical feature of Airport is that applications can interoperate. And in order to interoperate, they have to be able to talk to each other. This is where Airport provides an API layer that applications can invoke on each other, and user interfaces can invoke on applications. Applications can query data that belongs to schemas of other applications. Applications cannot make persistence calls for the data that belongs in tables of other applications. To save data that belongs to other applications, they must call the APIs of those other applications. Database transactions in Airport cross API calls. So the outermost API call will start a transaction, and all of the inner API calls will be included in that transaction. Each API call gets its own SQL save point. So that means that when a rollback happens due to an API call failure, it can be captured, and the error that was thrown by the API call can be handled while the outer transaction can still continue and be persisted. Airport client library passes in IDs for the UI and the user that are making an API call. Airport keeps track of this and other information in a request object. This request object can be accessed by the application APIs. Repositories are synchronized between devices via transaction logs. So every single transaction is shared between the devices that have this repository. Since multiple devices can modify a particular repository at the same time, there may be conflicts in the data of that repository. Airport automatically resolves those conflicts based on the timestamps of the modifications. AirBridge is a supplementary effort that provides airport integration solutions. Initial AirBridge projects are a private blockchain, single sign-on solutions, data transfer and storage platform adapters, and a unified validation solution. AirBridge validation is a declarative, entity-based way of validating inputs that come from the client. It is more concise and readable than procedural code. Using Airport's original state property, it will fail validation if there are property changes not specified in the validation definition. It will also limit the graph of changes to be persisted only to the validated entities. Same exact AirBridge validation definitions are usable on both server and client. The validator objects can be adapted into all modern UI frameworks and, where necessary, wrapped in input components. Airway is a set of peer-to-peer adapters for Airport. People using the same repository should be able to connect to each other directly and receive real-time updates. Highway is an airport extension for globally shared data. With Highway, popular airport apps will be able to have a centralized component without having to write custom server-side logic. Highway optimizes read data flows by retrieving transaction logs from NoSQL databases and executing queries on user devices. The write transactions are executed in a controlled environment on the server. Entity adapters will handle full-text search and maintenance. Highway is a transitional step between the world of decentralized databases and the Internet of Databases. Maglev builds on top of Highway. It takes processing of repositories to a trusted network of execution nodes. This allows to combine repositories from multiple data providers and provide truly global, cross-organizational data views. Data can also be modified transactionally across multiple organizations and jurisdictions.